The slide is looking at collagen type 1 synthesis and degradation, but we're going to talk about collagen synthesis in general. Fibrillar collagens have a triple helical conformation, or 3D shape, made up of 3 chains of 1,000 amino acids, each which intertwine, like in a rope. One of the remarkable aspects of collagen is that glycine occurs at every third amino of each alpha chain. Each chain is designated glyxy, where X and Y represent other amino acids, most particularly proline and hydroxyproline. Proline and hydroxyproline are important in collagen structure because, as each possesses a ring structure, they make the triple helix rigid. Glycine is essential in the folding of the triple helix because, as the smallest amino acid, it allows the 3 chains to fold in close proximity, something that would be prevented by any other amino acid because of the presence of a bulky side chain. Type 1 collagen is the most abundant collagen in animals, serving as the major protein of bones, skins, ligaments, and tendons. Collagens are synthesized by fibroblasts and some epithelial cells in the rough endoplasmic reticulum as soluble precursors known as procollagens, composed of 3 pro-alpha chains, 2 pro-alpha-1 encoded by col-1A1 and 1 pro-alpha-2 chain encoded by col-1-alpha-2A2. As the pro-alpha chains are synthesized, the N-terminal end, the first part of the protein synthesized, bears alpha-free amino group, moves inside the RER, the rough endoplasmic reticulum, where hydrophobic signal peptides of approximately 20 amino acid residues that direct the growing chain inside the RER, cleaved by signal peptidases. Inside the ER, selected proline residues are converted to hydroxyproline by the enzyme prolyl-4 hydroxylase. The enzyme requires ascorbic acid as a cofactor, accounting for the poor wound healing that characterizes scurvy. Hydroxyproline makes a major contribution to the stability of the triple helical structure of collagen because it maximizes hydrogen bond formation among the 3 chains of the rope-like structure. Supplementing these hydrogen bonds are interchain hydrogen bonds involving the amide groups of glycine and the carbonyl group of the amino acid in the X position, glyxy, of an adjacent chain. Further underscoring the importance of glycine is the fact that glycine alone, with only alpha hydrogen as its side chain, with only a hydrogen as its side chain, can fit into the limited spaces where the 3 chains come together. If glycine is substituted by mutation, the resulting triple helix will not be stable because hydrogen bond formation has been hindered. Selected lysine residues are hydroxylated by lysyl hydroxylase, and many of the resulting hydroxylysine residues are further modified by the addition of glucose or galactose and glucose, a process referred to as glycosylation. Once hydroxylation and glycosylation have been completed, the pro-alpha chains are poised to form procollagen, a precursor of collagen that has a central helical region flanked by non-helical amino and carboxyl terminal extensions. These propeptide extensions differ from the helical part of the molecule because they are not enriched in glycine, proline, and hydroxyproline. Procollagen formation begins with creation of intrachain disulfide bonds between the C-terminal extensions of the pro-alpha chains. Once the intrachain disulfide bonds have formed, the 2 pro-alpha-1 chains and the single pro-alpha-2 chain become intimately associated, and formation of the triple helix occurs with closure of the helix, starting at the carboxy terminal end and propagation of closure continuing to the left towards the N-terminal end, much as in the closing of zipper. Thus the terminal non-collagenous domains are the sites where the 3 alpha chains bind in register to undergo self-assembly of the triple helical precursors. A key factor in this mechanism is the C-terminal and appears to be hydrogen bonded interactions of hydroxyproline rich sequences.